So greetings students and welcome to the next video by Quant Masters here. So in today I'll be your technical trainer Shashank, and we will be going through what would be the possible questions that could be asked when it comes to TCS Digital round 2 interviews on data structures and algorithms particularly. So let us begin this without any delay. Now, there may be a lot of students who may think data structures and algorithms are pretty huge topic when it comes down to this, and it's going to be pretty difficult to study over time. So here's what we need to know when it comes down to this. If you're planning to code, if you're planning to implement data structures, then yes, it is somewhat difficult to do that. But when you start to work on, and when you start to work with particular theoretical or verbal interviews where more things you will be asked will be logical questions, you won't necessarily be asked to create a code of linked list directly in front of the interviewer. Most of the times you will expect something like, when it comes to data structures and algorithms, what are the different kinds of data structures, where are they used in real life, how do you use them, how is it efficient, why is it inefficient? These are certain questions that we may expect when it comes down to this. Followed by this, when it comes to algorithms, you will expect, if there is a certain problem, what algorithm would you choose to solve it, or how would you choose, or how would you use a particular algorithm to solve a real world problem. So these are certain questions that you may expect when it comes down to this. So let us begin without any delay and start learning what exactly this is, what exactly is data structures, algorithms, and how do we start to work through it so that we will be able to answer all the interview questions properly within this. So to begin with this, the first thing we need to know is, as always, what is a data structure? Before we begin to understand the types of data structures, and before we begin to work with data structures, we need to understand what are the types of data structures that you will be looking at, or you will be facing in your practical examples. So to begin with, the basic idea is that whenever you have something called a data structure, it's not necessarily that it's a new data type or anything like that. The basic definition or understanding of a data structure begins like this. It is a way of organizing and storing, or way of organizing, storing, retrieving data. Basically, that's it. So you can store data in many different ways. How exactly are you storing it? How exactly are you retrieving it? So there are different methods to do that. So those methods or those ways are basically what come up as data structures. So with this basic idea clear, let us look at a few of the common data structures we see in our everyday life, and what are they, why do we use them, how do we use them, and so on. So when you think about things, let's start with a simple thing. If I want to store 10 elements, I need to store them in a particular way. So what I do here is, to store 10 elements, I take up an array and I store all these 10 elements in continuous memory of an array. So this is a way of storing and retrieving data. So basically, a simple array is also a data structure. So the way of storing data within an array is that we are storing it in continuous memory allocation, and we are retrieving it from the addresses as required. So there are a lot of different data structures like these. We'll just look at a few of them. We have arrays, we have stacks, queues, linked lists, and trees. These are the major data structures that we know of and we use. So let us look at each one of these and let's see what exactly is the advantage of them, what exactly are the disadvantages of them, where should we use them and where we shouldn't use them. Because what I would expect is that when it comes to data structures, the major questions you will get are from data structures in terms of what is the efficiency of them, how do you use them, how are they efficient, why are they efficient, and so on. So I have one question by the time: what is difference between DS and DBMS? See, just to answer that, I'll just try to answer this in short. See, data structures are just a way of organizing and storing and retrieving data, basically. Your DBMS is also a database management system where you store and retrieve data. But this is particularly with a certain way. In other words, you're using this to create a huge set of data which will be used either in tabular form or non-tabular form, as we have seen in our earlier sessions. Whereas data structures are different methods so that you can store data efficiently. Efficiently in terms of time and space. The importance here comes only with time and space. You should make sure that whatever you're storing is efficiently stored with respect to time as well as space. So we'll look at how each data structure is different. That will give you a much better idea. So I have one more question. I have executed one completely and one partially. Yes, we may not, we will see how exactly it may turn. And we'll make sure to see how exactly it turns out and look at how others have done. It can't be guaranteed that just because you have executed one fully means that you're definitely going through. It depends on how others have also executed as well. So there's a lot of factors how in it. So my guess is not to lose hope until you do get the results. So let's go ahead with this. So the basic idea from here, let's begin here. So when we talk about data structures, we have a lot of different data structures. Let's begin with the first one when we talk about an array. So when we talk about arrays, this is the best way to understand the complete difference between them. Observe this very clearly, guys. So let's say you have 5 elements. We know array indices starts from 0 to n minus 1. So let's say array indices are 0 to 4. Yes, graphs are also data structures which we'll go through further on. As one of you pointed out, yes, that is also true. So we will see in graphs there are multiple types of graphs, there are multiple types of trees, there are multiple types of linked lists, there are so many combinations of them. Yes. So going ahead, I have one more question from Pujita. The same question I've answered with Subhashri as well. Depends on how others have done and how many people they are taking and what is their cutoff. So you never know. So it's best to wait till the results. So going back here, let's assume I'm storing elements, let's say 5 elements over here as 10, 20, let's say 30, 40, and 50. Now, over here, all that we're going to get is when you're storing the 5 elements in a simple array, which is in a continuous memory allocation. So one after another, we basically know how it works. Now, the thing about data structure is each data structure, this is the main point we should know before we go on to differentiate. Each data structure has a different capacity, or in other words, has different features when it comes down to the amount of time taken to store or retrieve data and the amount of memory taken to store data. So both of these matter a lot. In some situations in real life, you may not mind more memory being taken. You just have to make sure that everything happens in the shortest time possible. In some other time, In some other cases, time may not be of the most efficient scenario, but memory taken to make sure that it is stored in the smallest amount of space may be of more importance. So depending on these situations, depending on these scenarios, depending on um, what your use case scenario is, we will be using different data structures in different cases in real life. To understand that, let me just take this for instance, and I'm going to take this in such a way that we're going to compare arrays and linked lists first, so that we get a really good idea of how these two are exactly the opposite kind of data structures we may use. Now, before I go ahead with this, I just want to know one thing from all of you guys, from everyone who has joined in. Which branch are you from, and how's your level of data structures understanding? If you guys can state which branch are you from, and whether you guys know data structures well enough or not well enough, whatever it could be, you guys can just state that we're from ECE branch, and data structures, I know it 1 out of 5 or 2 out of 5 or 5 out of 5, whatever it could be. Just state this much. That would help out a lot, so that I can make sure to explain in as detail as possible, depending on how much you guys already know. That would help out a lot. So just state something like, if you're from mechanical, just state mechanical data structures out of from 1 out of 5. If you know the least, just 0.1, or if you know the highest, just 0.5. Basically, that's it. That's all I need you guys to let me know. So make sure you guys do that. So by the time, let's go ahead with the very basics here. See guys, when we talk about arrays, see, everything is stored in continuous memory location. So if the first value is stored in, let's say, address 100, second value, let's say, is stored in some address 102, then 104 and 106 and 108. Let's say it's stored in memory locations like these. Here's the basic idea. In this case, if you want to access any memory at all, any value at all. If I want to access a of 0, I know the starting address, I can just access 100. If I want to access a of 5, or sorry, a of 4, all I need to do is add 4 sizes to 100. I can directly go to that address and access it. I don't have to go through each value to get to the last value. So accessing any element is easy. So this is the basic idea. Accessing elements is easy. So in terms of time, what I mean to say is, in terms of time, accessing elements are easy. So to understand how we need to express these, because if we feel accessing elements are easy, we need some features, some parameter to express it. So the way we express it is generally by something called space complexity and time complexity. So these are the basic cornerstones. I'll repeat, students, these are the very basic things that we need to know. Like, what exactly is time complexity? How does it work? What exactly is space complexity? How does it work? Without this, the entire concept of data structures to be understood is always difficult. So when we talk about time complexity, there are basically 5 methods to denote it. So those 5 methods are something called big O and big omega, big theta, and then little o, and then little omega. So little o and little omega are something we don't usually use at all. So in most of the cases in real life, we only see these 3 things. So the basic idea is, any expression that is specified as big O expression, it indicates worst time complexity. That is, what is the maximum time we can take to perform some action. Similarly, big omega and big theta come up in different scenarios. So big omega gives you the best time complexity, and big theta gives you average time complexity. To understand this better, let me just take a very simple scenario. I am looking at the comments as well, and seeing that a lot of us are from different branches and we are not very good at data structures. So instead of just explaining with this, let me just take a small example so that you guys can understand very easily. Let's say this is your home and you want to go from your home over to no, it looks like a monitor screen. Don't worry about it. Let's say you want to go from your home over to let's say some other place, let's say B. So if you go from your place over to there, you need to figure out what time you should leave, what time you should reach there. So the basic idea here is something like this. If you're going at a peak hour where the traffic is highest, you know that the time will be worst time to reach there because the traffic is at its peak. There could be a lot of traffic signals and everything. So this worst case complexity is denoted as big O of the time. So the time may be 10 minutes, time may be 20 minutes, or whatever it could be. That we call it as big O. Similarly, when you look at the other two things, you have big omega and big theta. Big omega is where there's no peak traffic, you're leaving at something like 5 a.m. or something like that, where there's no traffic signals also, and you may reach in just 5 minutes. So that we denote as big omega of your time complexity. Could be 2 minutes, could be 5 minutes, could be anything. And theta is the average time. Now here's the thing, I told you guys one thing, that is big O stands for worst case time complexity. That could be 20 minutes or 30 minutes. What if your vehicle breaks down? We did not see that assumption. In that case, you won't be able to reach there at all. So that is also considered as a part of worst case time complexity as well. We will see how to perform or how to use these time complexities in each of these data structures to get a better understanding of them. So the first thing, let us go on to arrays and linked lists, and let us look at what exactly are the major differences in them first. So we already know arrays are where elements are stored in a continuous memory location. This is the basic idea of it. Now here, when you talk about time complexity, we see the following things. This is where we need, again, please note guys, I'm going slightly slower to begin with here so that all of you, because many of you are from different branches, and all of you can go through this and understand this easily. So the idea here is, you may require certain amount of time to access an element, or time to search an element, or time to delete an element, or time to insert an element. So these are the four things we generally look at. So what is the time to access, to search, to delete, to insert? And when we look at this time, we always measure it in worst time complexity. We never measure it in best or average time complexity, because we always are concerned with, in the worst case, how much time will it take. So let's look at this. If I want to access any element, if I know the index, if I want to access any element, let's say if I want to access a of 4, do I need to go through first element to second, then third, then fourth, then fifth? Is that the way to access fifth or the index 4? Or once I get to know a of 4, I can directly go ahead and access a of 4. I can directly go ahead and access a of 4. I think you guys would agree with this. So in this case, what happens is, since you can directly go ahead and access a of 4, the time complexity, worst case time complexity, is just 1. So if I want to access a of 0, it will directly go ahead and access index 0. If I want to access a of 3, it will directly go ahead and access a of 3. So to access an element, worst time complexity I have is big O of 1, because I only need to do one operation. This 1 represents number of operations you have to do. So I only need to do one operation here to access that element. That's the basic idea, guys. I hope that makes it simple and clear. So with this idea, let us look at the time complexity of different things. Now let us look at time complexity to search an element. If you want to search an element, let's take the same thing, big O. And here, if I want to search an element, let's say 50. Now, how will I search whether the array has 50? I'll first search if it has 10. If the first element is 50, if not, if the second element is 50, if not, if the third element is 50, if not, if the fourth element is 50, if not, if the fifth element is 50. So once we keep on checking each element, whether it is 50 or not, we will be able to find out whether we are able to search for that element or not. So what is the worst case complexity? How many elements should I search if I'm searching for a value which is not present in the array at all? Let's say I'm searching for a number called 70. Is 70 present in our array? It's not at all. So how much operations should I do? Is it 1, 2, 3, 4, 5? Can you guys let me know? So yes, basically, if I'm searching for an element, let's say 70, I need to first start from the first element, search all 5 elements. So I basically need to do 5 operations. If I do 5 operations to search for this element which is not there, the worst case complexity we get is we need to do 5 searches. In other words, for n elements in an array, the number of comparisons I need to do or number of operations I need to do is n. So we basically say that the worst case complexity for an array to search an element is big O of n. This is the basic idea. I hope that makes it simple and clear. So let us quickly go through and look at what would be the time complexity to delete and insert an element. So think about this, guys. If I want to delete an element, if I want to delete the last element, it's easy for me to do. I can directly remove it, no issues. But that's not the worst case complexity. We need to calculate big O. We need to calculate worst case complexity. So what we're going to try to do here is delete the first element. If I'm deleting the first element, my first operation is to delete this element. Second operation is to move 20 over to that space because first element is deleted. Third operation, move 30 over. Fourth operation, move 40 over. Fifth operation, move 50 over. So these are the basic ideas, or these are the amount of effort we need to put up to perform this. So the idea here is, in short, guys, to insert, or sorry, to delete an element, in the worst case complexity, worst case scenario, if I'm deleting first element, I again need to perform n operations in total. So even to delete an element, my worst case complexity is n. Now let us look at the last one finally, to insert an element. Now let's say I want to insert 10 at the starting of this array, but can I insert in the previous index of -1? I cannot do that. To insert 10, I have to move all the currently available elements one step to the right. So let us move them. Let us move 50 one step to the right. Let us move 40 one step to the right. So those are 2 steps. Let us move 30 3 steps. Let us move 20 4 steps. Then let us insert 10 5 steps. So for an array of 5 elements, I again need to do 5 steps at maximum to insert an element. To insert element at the end, that will be the best case. Only one operation is to be done. But to insert element at the start, I need to do n operations again. So the idea here is that to insert an element as well, you need to do n operations. So this is the basic idea of a linked list. Now, if we look at this, where can we use array in real life? Wherever deleting and inserting are not common, but accessing and searching, accessing could be common. Wherever we don't need to delete and insert elements again and again constantly, there we can use arrays. But wherever we may need to delete and insert arrays very commonly, we can't use arrays because it takes so much time. So instead, we will look at something called linked lists, where elements are not stored in a continuous memory locations. To understand, let's look at this And let's see how linked lists go and take the advantage of the concepts of arrays, and they are better when it comes down to time complexities with deleting and inserting elements. So let's look at this. Think about this, guys. Let's say this is an element 10. Now, if they're not stored in continuous memory allocations, 10 will be stored in some memory location. Let's call it 100. Then you'll have 20 in some memory location. Let's call it 200 for our easy understanding. And then there's one other element, let's say 30, which is stored over somewhere else. That is stored, let's assume, in an address 300. So when all these three are stored in different memory locations, the idea here is I can't know from to which memory location I should go next to access second element. So to do that, each element or each value here should not consist of just the element. It should consist of the next element address as well. So when I reach the first element, I will get to know where my second element is. I will go to that address, access the second element. Likewise, in second element, I should also store address of third element so that I can get to know where the third element is and go to that address and access the third element. So similarly, if my third element is the last element, we know there's nothing ahead of it. We just call it as null followed by this. So this is the basic idea. So when we look at this and try to work through this, the basic idea is each element stores more data or requires more memory. So the space complexity here is more. The space taken for each element is more than what it is for an array. But the advantage is they're not stored in continuous memory allocations or continuous memory locations. So I can create any variable at any space and add it in between. Take for example, I want to create an element called 15 in between 10 and 20. So I will take 15. We'll store it in some random location. Let's call it as 1500 is the location where 15 is stored. Now, it should point to 15 and then 15 should point to 20. So all that we're going to do here is the address of 20, whatever it is, 200, we're going to store here. And the address of 15, whatever it is, 1500, we're going to store it over here. So are we shifting multiple elements over here one at a time? We are not doing any such shifting of elements. All we are doing is taking one new memory location, adding an address in it, adding another address here. That's basically it. So this is where you can say that the time complexity spent here is much lesser. So the idea is to insert an element. Time complexity spent here is 1. Now, you may wonder, why is it 1? Because worst time complexity cannot be 1. We are doing multiple operations here. We are making sure that this address is changed and this address is changed and this value is stored. So time complexity, we generally measure it in terms of repetitions of a loop. For example, if I want to search an element in an array, I will do the following logic. So things like for I equals 0, I less than equal to n minus 1, I plus plus. I need to search all the elements. So the maximum time this will run for is n times. That is why we call it as big O of n. Similarly, when we talk about linked list, we don't use a for loop to run repeatedly at all here. We just have a set of statements which executes only once. So whether you try it to insert at any possible location, any possible way, the number of steps that will execute are basically same. They're basically executed at the exact same point here. So once this is understood, we can now state that it's simple to just state the following. So the worst time complexity here to insert an element is 1, because we are not going through a loop to shift all elements ahead or to shift all elements behind. So you can say worst time complexity. Again, I'll just copy this. To insert an element is 1. Now let's look at the worst time complexity to delete an element. So when you talk about this, the idea is if I want to delete this element, all I need to do is just remove this from memory, and instead of this next address pointing to 1500, I just have to make it point to 200. That's all. So I'll just remove this and make it point to 200. So now it's pointing over in the same way that it's supposed to. So the basic idea here is simple. To delete an element, I'm not again shifting elements one before another or something like that. It's pretty simple. All that we are doing here is just deleting one element, changing the value in the memory location of another. So this basically helps us delete an element. So we're not doing n steps, or we are not repeating the step n times. It's just one time, basically it. That's all. But when you talk about searching an element, can I search an element in just one step though? Can I search for an element in just one step? If I'm finding 20, can I directly go to this and get 20? If I'm finding 30, can I directly go here and say I found 30? I can't do that here. If I want to find 30, I need to first check if first element is 30. If not, I need to go to next address, check if next element is 30. If not, I need to go to next address and check if next element is 30. If it is, then I'll stop. So the idea here is to search, you still have to do n operations. That does not reduce at all. That doesn't change in any way whatsoever. So the idea here is, for searching, it's still big of n. But let's look at time to access an element. Now think about this, guys. If I want to access third element, can I directly find address of third element and access it? I just can't, because it's not an array. If it were an array, I would know it's all stored in continuous memory location. I can directly go ahead to a certain element value. It's basically that if you can get a simple idea that you are accessing third element in an array, you know that it's stored in continuous memory allocation. You can directly find the address of third element and access it. But when it comes to a linked list, you can't access third element directly. You need to first access the first element, find the address of second element, go there, find the address of third element, go there, and access the value of it. That is the basic idea, guys. I hope that makes it sound simple and easy. So to access an element also, we are having big of n. Now you can see a little differences already here. So in arrays, to access any element, if you want to access 100th element or 1000th element, whatever it is, it's not difficult. Worst case complexity is just one. It's just one. Whereas in case of linked list, worst case complexity comes up to be n to access an element. So the disadvantage in linked list is accessing elements is costlier in time. It takes more time to access elements. But if your main work in a to use a data structure is that you'll be inserting and deleting elements a lot generally, then you can use linked list. That is the basic idea. So this is the simple concept of what exactly is a data structure. How do we measure the time taken to perform different operations when it comes down to data structures, and what are the most common data structures we can have. So when you look at this, you may need to start thinking, where do we use these things? So when you talk about array, we use it generally whenever it's a continuous memory allocation, like a queue or a stack. For all of these things, we generally use array because they are limited in length and the major work is not so difficult. But when you talk about linked list, when it comes to real life, think of this. Think of an image viewer application in your phone. In your phone, an image viewer application, when you swipe left or let's say swipe right in an image viewing application, the idea is that you're going to a different image in a different location. So the image viewer should know what is the address of the previous image and what is the address of the next image. These are some kinds of examples where you basically get to use them in real life. So going ahead with this, let us look at now the data structures like stacks, queues, trees, and graphs. And once this is done, we will take a little look at what is dynamic programming before going ahead with the major concept, that is algorithms. Now, let's begin with the very basics of this, guys. Think about this. Um, I have noted that most of you guys are from ECEEE mechanical branch and so on. So I'll try to explain stacks from a little basics for you guys so that you guys can understand the kind of questions that can be expected and what exactly you need to do in order to answer them. So observe this clearly, guys. Observe this carefully. So the basic idea we already got to know in terms of linked lists and arrays. So stacks and queues are generated with arrays. Trees are generally created with linked lists. Graphs, depending on the situation, we either create it using array or linked list. So let us begin with stacks and queues. Think about this, guys. You have a CD stack. When you talk about a CD stack, the first disk that you insert, and then let's say you insert second, third disk or so on, and fourth disk, you can't take out the first disk right away. If you want to take away the first disk, you have to take away the fourth, the third, and second disk before it. So the idea here is whatever is inserted first or whatever is first in to the stack is only last out of the stack. So I have a question: is the theory enough? I mean, no programming? No. To answer that, programming is very majorly required. I will be going through a little bit of the programming part as well to show you how exactly it works and how exactly we use it in terms of code as well, because you need to know this. Because when you talk about concepts like linked lists, they will ask you, how do you create a linked list? What data type do you need, or what data type will you have to create a linked list? You can expect such questions. So I will be going through that in detail when we start about linked lists in detail and then trees in detail. But for stacks and queues, since we are basically doing it from arrays, I'm not going into coding much. I hope that is clear. But I will be going into the coding part, particularly from linked list. So not to worry about that. So the basic idea of stacks here, guys, is think about this. You just need to have an array where whatever is inserted first is removed last, and whatever is inserted last, that is we call it as last in, is removed first. So stack is also called this, a first in last out data structure, or you can call it as a last in first out data structure. So the basic questions you can expect when it comes down to stacks is, what do you mean by stack underflow and stack overflow? This is a very basic and common question that you can expect. So I'll repeat, guys. The questions that you can expect again when it comes to data structures, let me repeat this to make it clear, are that you can expect questions on time complexity of each data structure. That is, how much time would it take for a particular data structure to perform something, like whether to search, whether to insert, whether to delete, whatever it could be. Similarly, where is it used in real life, and what are the particular cases you encounter when it comes down to this. So let's look at this as quickly as possible. So when we talk about stacks, think about this, guys. Think about a simple array. Let's say you have 5 elements in this array. Since it's a stack, you know that whatever you insert at first, it can only be retrieved at last. So if you keep on inserting elements like this, the first element you can remove is always the last element. But before this, if you try to insert one more element like this, it can't be inserted into a stack because this stack has limited size. It will just overflow and exit out of the stack and just fall off the stack. This is just called stack overflow. It's not something huge, it's not something complicated, it's something simple that we just need to know is that when you try to insert into an already full stack, it's just called stack overflow. Similarly, when you try to delete from a stack which is empty, you can't delete anymore, that is called stack underflow. So similar to this, you have certain terms that you need to know when it comes down to stacks as well as queues. We will look at these terms, we will look at these particular concepts, and then we will go ahead with the major part, that is queues, and the very important part, trees, graphs, and algorithms. So the basic idea here, guys, please note and remember this: stack can be created using linked list or arrays, up to us, completely up to us. So stack overflow is when we try to insert into already full stack, and stack underflow is where we delete from already empty stack. And in stack, to insert into a stack, we generally call the function as push, and to delete from the stack, we generally call the function as pop. That's the basic idea. That's just the basic things we need to know. So you can just create a simple function where if the stack is empty, insert an index 0, get to know your new index is 1, then insert at 1, then when you're inserting again, increase the index, insert at next, then when you're inserting again, increase index, insert at next, and so on. That's the basic idea. But let us not focus much on these. Let us directly go on to time complexities. They will ask, okay, you guys know data structures, so you know data structure. So when you talk about data structures, what are the common types? Then you'll answer something like, we know stacks, queues, are linked list, trees, graphs, everything. And they'll ask, okay, you know stacks well, so what is the time complexity for stack? What is the time complexity when you search for an element in stack, when you insert an element in stack, when you delete an element in stack? Same thing can be expected as questions here. Think about this, guys. When you have a stack, if you're inserting an element, how much work are you doing? Just one work, inserting here or inserting here or here or here or here. Worst case time complexity is also one, because you can't insert at the start of the stack, you can only insert from one end of the stack. So when you're inserting from that end, you're inserting in the first place itself. So worst case time complexity to insert is 1. Similarly, when you're deleting, we can't delete the last element and move all elements before, we can only delete the topmost element. So when we are deleting the element also, basically 1. So like this you can find out time complexities generally. So these are something you guys can go through, can learn. My suggestion is, when you're learning through for this, just before interviews, you guys can go through cheat sheets, you guys can go through some cheat sheets that are already there. So there's this good site for your reference that is called bigocheatsheet.com. So it's got its own PDF which is good enough to use. So it lists all the time complexities for every data structure, from arrays, stack, queue, linked list, all kinds of trees, everything. So this is one thing that I would suggest you guys to just go through, because we have all sorting array, every complexity. We will see complexities of sorting arrays, sorting algorithms as well. But the basic idea, just remember, guys, you need to know worst case time complexities to access, to insert, delete, and search. These are the most important things to know. So they have listed here for access, search, insert, and delete when it comes down to stack. So anyway, let us move ahead from here. So for this, I'll just provide you guys with the reference of the PDF that will be obtained here. and I'll be sharing this link at the end as well, because I'll repeat, time complexities are a huge part. And since we already got to know how to calculate time complexities from arrays as well as linked lists, let us not go in depth in it, because the more we go through it, the more time we spend through it again. And since we already got to know a few basic stuff, let us directly move ahead to queues. So guys, think about this. There's a lot of times in your case, you may have seen flash sale where it's only that something is available for just 1 rupee, like a new phone or something like that. So what you do, if it's at 12 p.m. exactly, let's assume they say that only first 5 members joining or clicking the link will get the mobile phone. So you will just wait to click buy link. So when you click it, here's the thing, there will be a queue. So the first person who clicks the link comes up to the first person in the queue, second person here, third person, fourth person, fifth person. If you're coming up after that, you may not win the first prize. After 5 people, the rest may win the second prize or something like that. You may get the second prize or so on. So these are some real examples of queues. So the first question that you can expect is, where we use queue in real life. Think about this. The most common example you can see is flash sales online, where first 100 people clicking the link will get a certain price, second 100 people clicking the link will get a certain different price, and so on. So with this, you can say that queues are used in real life, or I'll just type it as used IRL in examples like flash sales or online ticketing systems, where only if the seats are limited, only those many tickets can be sold. Later on, anybody who tries to click buy later on, they won't be able to get it. That's the basic idea. But where do we use stacks? Where do we use in real life stack anywhere if such a question is asked? Think about this, guys. Let's say I have typed 1, 2, 3, 4, 5, 6 here. I want to delete the last thing that I've typed. The last thing that I've typed is available in my undo stack. The last thing that I've typed will be available there. Moment I press Ctrl Z, the last thing I've typed is removed. Then again, then the one before that, 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 before that, before that, before that, and before that. So every time I press Ctrl Z, whatever I have entered at last will be removed. So let's say this is stack. I've inserted 10 at first, I've inserted 20 at next, then I've typed 30. So whatever I've typed last that is on top of the stack, that will be removed the moment I press Ctrl Z. Then the next stop, then the next stop, then the next stop, then the next value at the top, then the next value at the top. This is the basic idea of where you can just state that stacks in real life are used in undo or redo for all your Word, Excel, and browser access, everything. So for all these purposes, we basically do this. So I have one question. Could I explain time complexity with an example? See, time complexity, we took a few examples here, particularly for arrays as well as linked lists. If you want me to take up time complexity example for something else particularly, you can let me know. I'll make sure to do that, whether it is for queues, particularly to access, to delete, insert, or anything you want to know, you can let me know. But I would suggest this link would basically be good enough for us to learn as well later on. So let us look at the next part. See guys, when you talk about queues, the basic idea is, in a queue, I'll just give you guys a simple example, because even as a computer science students, this is something we go wrong at many times. So this is something where we need to learn where exactly are we going wrong and how to answer this correctly. Think about this, guys. Let's say we have a queue of 5 elements. So let's say the queue has some numbers like 1, 2, 3, 4, 5. Now, if the first person is out of the queue, we don't just delete it. What we generally do is, we have two pointers, one pointing to the front of the queue, another one pointing to the rear of the queue. We generally call these variables as front and rare in simple words. So any tutorial you may go through, you basically get the same thing. So front indicates the index where the first element is stored. Rare indicates the index where the last element is stored. Now, every time I, let's say, insert an element, the rare of the queue is supposed to increase, and then I'm supposed to insert here. So I can get to know what is the length of my queue very easily. That's the idea why we use this. Now, if I want to delete an element from the queue, I'm supposed to delete the first element, and I'm supposed to switch or move 2, 3, 4, 5 all in this location. But in a simple queue operation, that doesn't happen. In a simple queue operation, if you're deleting the first element, you're just moving front ahead. That's it. If you're deleting second element, move front ahead by one more value. If you're deleting third element, again move it. If you're deleting fourth element, again move it. When you delete fourth element also, front and rear point to same location. When front and rear point to same location and you're deleting that element, they will point to -1, stating your entire array is your entire queue is empty. That's the basic idea. But where queues fails miserably, it fails, is in the following condition. Observe this very clearly, guys. This is where queues fail, and this is where most of us don't generally realize this. See, if I'm deleting first element, front gets increased by 1. So the length of my queue is just this. So this person is at the front of the queue, this person is at the last of the queue. Likewise, if I delete second element, we already know front increases, so this is my queue. Now, the thing is, if I try to insert an element here, we know that in our queue there are only 3 elements, but the maximum length here is 5. So I should be able to insert 2 more elements here. That is basically 1 and 2. But the problem here is rare points to the last index, 4. Front points to some second index. And I can't insert in previous values. I can only insert at the end of the queue, not at the start of the queue. So the concept of queue fails when you delete a few elements and you try to insert. Even though the queue is not full, I can't insert here because we can only insert at the rare end of the queue. I hope this is something that you guys are able to just understand. So to solve this problem, we use something called circular queues. Think about this, guys. Right, I think this is better. Perfect. So think about this. Let's say we have index 0 here, index 1 here. Let's say we'll just call it as index 2 here, index 3 here, and index 4 here. So if, let's say, we have deleted first 2 elements, you have 30, 40, and 50. In a circular queue, even though you have deleted first 2 elements, let's say we have just moved front. In a circular queue, front will point to index 2, rear will point to index 4, just like our previous example we took. Observe, guys, just like the previous example we took, front points to here, rear points to here. But now, since it is circular queue, I can increase rear here, which will go to 0. So when I increase rear here, I can go ahead one more value and insert my next element. Let's say, for example, 60 here. I'll just delete the previous element. Let's say we insert 60 here. Then if I want to insert one more element, all I need to do here is just increase rear by one more. And when I increase it, rear will now point to 1. And I can insert my next element, let's say 70 here. But after this, I can't increase rear again, because if I increase it, I'm reaching front. That means queue will be full. Front is starting from here, we are going all the way, and rear is this element. So in this case, queue is full. So this is the advantage of circular queues over just a regular queue. So in real life, if you ever want to use a queue, if you use a simple example of queue like we did before, the problem happens is when you delete some elements, even though the queue is not full, you can't insert any more elements. To do that, you need to use this concept of circular queues. And circular queues is where the basic idea is rare after it becomes, let's say, size 4, it will not increase up to 5 because 5 is the limit, 4 is the limit. It will instead increase after 4 back to the starting address. That's the basic idea. So this is the concept of circular queues, which is more efficient than simple queue created using an array. So circular queue, again, it doesn't mean that in memory it is stored in a circular fashion, because memory, everything is sequential itself. It is stored in a sequential fashion itself. But when rare reaches the maximum value 4, after this it won't increase to 5, it will instead increase to 0. So that's the only coding difference that you need to know in order to solve this. So again, there's a reason why we are not going through the code part of all of these, because there are so much that you can expect when it comes down to these topics, things like algorithms and linked lists, different kinds of linked lists, binary trees, binary search trees. There are so many questions you may expect. It is highly difficult that they will ask you to take a pen and a paper and start writing down a queue algorithm of uh, insert function of queue, delete function of queue, and everything. But if you know this basic idea, and if you really want to learn, this is particularly for everyone from EC, Triple E, and different branches. If you guys really want to go through it, learn it, and try it out, I would suggest you guys to make sure do that. So going ahead from here, let us now move ahead from this to linked lists, where we see, I'll repeat this, guys. This is where your real part of the crux or the core of data structures begins here with the concept of linked lists. So let's look at this. In a linked list, when you talk about first element, it doesn't store just an element, it stores address of next element, the second element also. So I have one question. What is the time complexity of circular queues? See, when you talk about queues and circular queues, basically the time complexity is same, because to insert you're doing same steps, delete you're doing same steps. Only difference you're doing is when you reach the end of the, when you keep increasing rare, when you keep increasing rare value from 2 to 3 or 3 to 4 or so on, you keep checking, have you reached maximum limit? If you've reached the maximum limit, you're just going back to 0. That's basically it. So here there's no difference in time complexity in queue and circular queue. It's just that circular queues are more efficient because we are just making sure that rare can go back to 0 as well. So that's the whole idea. I hope that makes it simple and easy for us to understand this. So let us go ahead here further on. So the next thing we may need to go through is something called linked lists. And here's the basic idea, guys. When you talk about linked lists, the basic idea of a linked list is, again, I'll just repeat this as quickly as possible. Each element has address of next element. Let's say the element is 100. It is stored in an address 100. It is 10. It will have address of next element. They're not stored in continuous memory location. In the next element, in the next address 200, you'll have the element 20, which will have again the next address 300. In that element, you'll have the, sorry, in that address 300, you'll have the element 30, whose next address is basically null. So in this case, your entire linked list stores elements in non-continuous memory locations, and we have also seen how exactly it works here because of the changes in time complexity with respect to arrays as well. Now, if we want to implement it in real life, a question that you can expect is, how are you going to be able to implement it? How will you store an element and an address together? So the basic idea is there is no data type which can store an integer element and a pointer together. You can't do that with any data type. For this, you need to create your own data type, or in other words, a user defined data type. That is what we need to create in order to solve this. So let's look at what is the user defined data type that we can use for this. So we use the concept of structures, where we can combine multiple data types together. An array can only store a single data type. Here the problem is we have an integer value and an address. Address size is not same as integer size. That's why we can't store it in an array. We need something different where each element takes a different size. So to do that, let's try to create our own structure. Each element will be of this struct type, which will have two elements within it. One is this data and another is the next address. So when you look at this, let's call this struct name as something called node or element, whatever you guys want to call. And the reason I'm explaining this is it's quite important to know that you can expect a question, particularly where they will ask you, okay, you know data structures, you know linked lists. All right, how do you create a linked list? In coding terms, what do you need to do to create a linked list? Because interviewers know linked lists are created in an entirely different method, so they will generally ask this. So the basic idea here is, when it comes down to this, I have a question. In a particular node of a linked list, what is the address of address node? Same as data. I'll explain this. So the basic idea here, guys, think about this. We are need to create a structure, our user defined data type, and we will create elements of this user defined data type further on. So I'll just use a semicolon at the end. So here we have two parts. The first is an integer element, so I can just state it's just an integer element. Let's just call it as data, or you can call it as value, anything you want. So this is the first part, that is clear. So we have our own data type which has two parts in it. The first part is an integer. After the first part, the second part is storing an address. Now the condition comes up as, what address is it? Because when you talk about address, if it's an address to an integer variable, we store it as int star. If it's an address to a float variable, we store it as float star. So my question to you guys is just one simple question: what data type should be the address of? Should it be int type? Should it be float type? What should be the data type of this address? We know we need to create a pointer, and that pointer we'll just call it as next in short, or you can call it as next underscore address, whatever you want to call it as. So the idea here is we'll just call it as next. So what should be the data type of this? Now the problem is, if it's a data type int, I can only point to this integer value. Am I supposed to only point to the integer value, or is this address supposed to point to this entire element? You guys can let me know this. What do you think? What should I do? Should I make sure this address points to just this element, or should I make sure this address points to this whole set of data? Of course, it should point to this whole set of data. So to make sure it points to this whole set of data, we need to find out what is the data type of this whole set of data. The data type of this is struct node. So the pointer here is storing address of another struct node variable. So the pointer here is supposed to be of type struct node. So this is how each element is created in a linked list. Each and every element of linked list is stored in a separate user defined variable that we create as struct node, and all of this has to be created dynamically when the program is running. If user wants to create one more element, when the program is running, it's supposed to create it. So I have one more question: what if we use void over here? See, the problem with void is you can't do anything with a void pointer. Void pointer has certain rules. The rules are, you cannot dereference a void pointer and get its value. Of course, you can create a void pointer, something like void star p. If you look at the rules of a void pointer, you cannot go to the pointer value. You cannot dereference it and go to the value within that address. That can't be done using void pointer at all. To make sure to do that, to make sure that you're able to dereference it and access the values, we use it as the data type that is available in that address, that is called struct node. At Su's question, I hope that is able to clear your answer, because if you have an integer called p equals 10, if I have a void pointer star q which is storing address of p, I can't access the data within it using a void pointer. That's the basic idea. So let us go ahead from this. This is how we basically create a linked list. So if you look at any linked list code, think about this, guys. When you look at linked list codes, they're generally 300 to 400 lines long, because they will have functions like insert, delete, search, reverse a linked list, find loop in a linked list, and all these functions are going to be there. So it's basically 300 to 400 lines long. So when you look at that entire code, you should never, this is one thing I would like to say to all the students, because most of us do go wrong in this. You should never by heart any code when it comes down to creation of these data structures, whether it is linked list, trees, graphs, whatever, any algorithms. The moment you by heart this or mug it up, it ruins the whole purpose of learning it. Here's the idea how you need to do it. If you're looking at insert function of a linked list, take one example by yourself. Write down one example by yourself. Read each of the line, whatever they are storing. Try to create your own memory location according to you. Okay, they're using something called temp. They're using something called I. What are they storing in it? What are they storing in it? And try to go through every line and try to figure out where what is being changed in your own example on a paper. That will help you understand what are the steps they're taking. Once you get to know the steps, you can create this code easily by yourself. That is where algorithms come up further on. The basic idea of algorithms are, if you know the steps to follow, you can easily convert it to code. That is the basic idea. So we'll look at that further on, but that is the basic idea you guys need to know. So when we talk about linked lists here, a common question could be asked is, where do you use a linked list in real life, which you have seen a couple of examples over here. So followed by linked lists, there are a few other things that you can particularly be asked. What are the advantages of linked lists when it comes down to this? What are the disadvantages of linked lists? So one thing you guys need to know here is, when you start using linked lists, things are not stored in continuous memory location. Advantage: if things are not stored in continuous memory location, memory overflow will not happen. Think about this, guys. Will I have 100 MB continuous memory in my RAM? I may not be able to, because somewhere in middle 1 MB may be used by something, somewhere in middle another 1 MB may be used by something. If that is the case, this total 100 MB cannot be used by my program for whatever purpose I'm using. But if I have a linked list, I can store each element in different location and use them. Although they take more memory, I can use it for larger locations, because in RAM I cannot find huge memory locations which is free continuously. I hope that makes it very simple in this case for us to understand. So I have a question here, that is, can we create a linked list using a class? So the idea, if you want to, you can. There's no problem about it. There's no problem with it. The thing is, for those who don't know, Java does not have structures. Java has only class. Java doesn't have the concept of structures and unions. So in Java, you have a concept called collections. In collections, linked list is basically an object of a class. where things are stored. So it's an inbuilt thing. You don't have to create it. So you don't have to think about create using a class. But in C and C++, structures are present. Since structures are present in C and C++, you can use the concept of structures within this. That's the basic idea. I hope that makes it simple and easy to understand based on the question that's just been received. So going ahead from this, let's go ahead and look at the next concept here, guys. So let's go ahead look over here. Now that we got to know what is the advantage of linked list, you may think like, hey, linked lists are better. There's so many advantages here. I'm going to keep using this in my real life further on. But think again, there are a lot of disadvantages as well. They are not stored in continuous memory locations. Since they are not stored in continuous memory locations, you can't access any element directly without going from one element to another. And if you keep on moving from first to second element, second to third element like this, you can't go backwards anywhere, because this element does not store address of previous element. This element does not store address of previous element. So this is the basic advantages as well as disadvantages. So you need to know where to use based on the purpose, based on the requirement. So here, if the last element, instead of storing null, it is storing address of first element again, it is pointing back to the first element. This is, of course, it's a loop, but it is also called a circular linked list. So this circular linked list can be used to create the concept of circular queues as well. If you need to create a queue where the length is not fixed, the length could be anything whatsoever, we can simply create a circular linked list and make a queue out of it. So this is one thing you guys can know as well. So linked list can be a circular linked list. So the basic idea, I'll just repeat, I'll just store it or type it here. The data type used or created for this is like this. You take a struct data type, you create your own data type here. Let's say call it as struct node. I'll just write it as quickly as possible for your reference. That is, you just have something like int data or int value, and then something called struct node star next. Now, once we know this basic idea of a circular list and linked list and a circular linked list, the next thing that comes up is something called a double linked list. So guys, the disadvantage in a linked list is when I'm going in a linked list from left to right, if I'm traversing a linked list, I can't suddenly go back to a previous element. That is basically impossible, because one element does not have address of the previous element. It literally does not have that. So to make sure you can go in the reverse order as well, here's what you need to do. Each element should not only store its next element address, but it should also store its previous element address. This basic concept is just called a double linked list. So think about this, guys. Very simple. You have 10, 20, 30. So all that you need to do in modifications over here is, before that, I have one question. What are the advantages of circular linked list over linked list? See, in a linked list, you get to know when you end the queue. When you end the linked list. I'll just not delete this. I'll take a different image so that we don't have to redo all the work that we have done so far. So think about this. In a linked list, each element points to next element and you get to the end of it, basically. But in a circular linked list, the last element points back to the first element. So think about circular queues that we had. Let's say this is the front and this is the rear. If you keep on, let's assume this is the front here and this is rear. If you keep on increasing rear, once it reaches end of a linked list, it can't increase again. The basic idea. Or even if it does increase again, you want to go back here or something like that. So you basically, all you need to do is just take it back to the starting location, reuse this location instead of deleting it and using another location and so on. So there are so many uses in it, but it's not like there are certain advantages only for it and disadvantages for the other thing. So that's the basic idea. But our major focus, let's go on to this. So a double linked list is where, let's say, this is stored in 100, this is stored in 200, and let's say 30 is stored, as we assume, in 300. So 100 here will store next address as 200, 200 will store next address as 300, 300 will store next address as we assume null, but 30 will store address of its previous element as well as 200, 20 will store as 100 as well. Since this is the first element, there's no previous element, you basically store it as null. So to create this, the only change you need to do in the data type is just take the same data type, but instead of struct node star next, you just need to create one more thing called struct node star previous as well. That's the only data type change that you need to do in order to create a double linked list. So if you look at this, what's the advantage here? So you can't just move forward, you can also move backwards as well. You can also move in the reverse direction. So you can traverse in any way you want. You can traverse ahead and you can traverse behind. So why would we need this? What gives us the advantage to use this, or where do we basically use this? The advantage of using this is, from double linked lists you can create trees. That's the basic idea. The basic idea is, from this we can create trees. But before we go on to create trees from this, there's a couple of things I just want to point out. See guys, you have already learned linear search and binary search. You guys already know linear and binary search. I assume you guys know this. So if you don't know this at all, please do let me know by a text over your live chat. If you guys, what I'm pointing out here is, in a linear search, you guys already know that you're searching from one end to the other end. In a binary search, you know that the array you have will be sorted. That is, you have 1, 2, 3, 4, 5, 6, 7, 8. Your entire array is sorted either in ascending or descending order. And if you want to search an element like 7, you're going to search the middle element, check if it's equal to 7. If it's not, whatever element if you're searching, if it is greater than this element, you'll go ahead of this and you'll cancel the rest of the previous elements. So I have got don't know as a few answers. All right, so I'll just point this out. Students, please note and remember this. In short, let's say we have an array which stores, let's assume, 10 elements. I'll just take it as 1, 2, 3, 4, 5 up to 10. So the basic idea here, guys, observe this. The basic idea here is, all right, we'll revise it, not to worry. I'll make sure to revise it. I've got more comments to just revise it. So the basic idea of a linear search is, it's also called a sequential search. It's where you start from left end to right end of the array. If you want to search an element 11, you're starting from first value. You keep on searching whether each value is 11. So you finally search till the end, and if it is not found, then you can say it is not found. Or if it is found, wherever you find, that is where you stop. So the worst time complexity you see here in linear search, if you're searching for an element, can you guys guess what would be the worst time complexity? Right, of course, simple. The worst time complexity here is, again, to search linearly is n, because if there are n elements, we need to perform n searches. So when it comes to linear search, before we go on to trees, because in trees we talk about binary trees, and binary trees is just an improvement of binary search. So that's why I want you guys to know binary search as well. So the worst time complexity to search in a linear or sequential search operation is big O of n. Now let us look at worst time complexity to search in binary search operation. So binary search operation basically works like this. See guys, I want to search for an element 11. Now to make sure that you are able to do binary search, your entire array must be sorted. If your array is not sorted, you can't do binary search. I'll explain with an example. You'll understand why it must be sorted. Think about this, guys. Let's say this is our entire array, and what we need to do over here basically is just this. If I want to search for any element, first thing I'm going to do is go to the middle element of the array. Let's take a look at this. How many elements we have? 10 elements. So I'll take indices as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So since we have 10 elements, just take number of elements by 2. You get index as 5. So you can take it either 5 or you can take it as 4 as well. Generally, we take it as something like this. I have one of you answering as big O of n by 2. No, that is wrong. I'll explain why it is not big O of n by 2 clearly. So that is where we are wrong. We go wrong when we think n by 2. I'll explain why it's not n by 2. So first we search within the middlemost element. If 11 is equal to it, it's not. Then we check if 11 is lesser than it or greater than it. Of course, 11 is greater than it, greater than 5. So that means we are sure that 11 does not exist in any of these locations. So in just one search, we have reduced our search area or number of elements to be searched by half. Then we'll take this array, that is 5 to 9, and we get half of it. What is 5 plus, that is from 5 to 9. What is 5 plus 9 by 2? That gives us 7. We'll check if it is equal to 7. It's not equal to 7. It is index 7. It's not equal to the value 8 in index 7. It must be greater than that. So we'll cancel even these. So again, we have reduced it by half in just one search. Now we'll take again 8 plus 9 by 2. That becomes 8.5. We'll take it as 8 itself. We are searching here. Is 11 equal to 9? It's not. So this also is cancelled. We'll go to the next one because it's greater than 9. We'll search in the last element. Is 11 equal to 10? It's not. So we have searched the entire array only with 4 searches. Previously, we had to do 10 searches. So the worst case complexity we get here is 4 for 10 elements. It's not exactly n by 2, but it's lesser than n by 2. I'll give you guys an idea of how it's lesser than n by 2. Think about this, guys. Let's say we have 32 elements. Now, if I have 32 elements, I'll search the middle of the 32 elements. Once I search middle of 32 elements, I'm cancelling out first 16 elements. I'm only searching in the next 16. First 16 is cancelled. I'm searching in the next 16. In the next 16, I'm going to divide it again as 8 elements and 8 elements. And I'm going to search if it is present in any one of these. That is, let's say first half, it's not available. I'm checking it in second half. You can even do it like this if this sounds easy. But in a diagram, it's going to be difficult to draw. So I'm doing like this. So in the second part, the first half has 8 elements, second half has 8 elements. When you search over here, it's also not big O of n by 2 minus 1. I've received one comment. It's not even that. I'll explain why. So when you search here, you're skipping one half of it. You're going to be able to search in the next half. So here, this 8, you will divide it again as 4 and 4. Again, here you're not going to find it in one half. You're going to go for the next half. Here again, you're going to divide it as 2 and 2. Here you're not going to find it in one half. You're going to go for the next half. Here you're going to divide it as 1 and 1. You're not going to find it in one half. You're only going to go for the next half. So number of searches we have done are 1, 2, 3, 4, 5. 5 searches are what we have done for 32 elements. So how can we relate 5 and 32? I can say, in short, to relate 5 and 32, 2 power 5 is equal to 32. So with this, the idea what we are going through here is, since 2 power 5 is 32, I can say the number of times I have to search here is the power of 2 for the number of elements. Remember guys, this is the number of elements. 32 is number of elements. So I can say if I get log 5 base 2, sorry, log 32 base 2, I will get 5, because 2 to the power of 5 is 32. So all I need to do is get whatever is the n number of elements to the base 2. So this method where we are dividing the array and then we are solving the equation, is also called divide and conquer method. In algorithms, we also call it as divide and conquer method or divide and conquer mechanism, where you're dividing the whole array and conquering each part of the array. So as a couple of you stated, it is big O of log n. When we say log n, we generally assume that it is log n base 2. So that log 32 base 2, you get it as 5. So whenever you are dividing any array or any data into half in each of the search, or with every search, if you're eliminating half the amount of data, you can say that time complexity is going to be big O of log n. That's the basic idea you just need to know. So here, worst time complexity to search in binary search operation is big O of log n. So here you guys are able to see that this is much more efficient. Think about this. If you have 32 elements, would you rather do 32 searches or would you rather do just 5 searches? 5 is easier. But the problem that occurs here, this is where the problem occurs. In an array, if I have something like 5 or 6 elements and I want to insert an element in between, my work is to perform binary search. To perform binary search, it must be sorted array. If I want to insert an element in the middle, I cannot insert at the end. If I have 1, 2, 4, 5, 6, 7, 8, and 9, for example, I want to insert 3. 3 must be inserted between 2 and 4. It should not be inserted anywhere else. So to do this, I'm going to find it difficult because I have to move every element by one location. So to solve this, what we're going to do is we're going to create a tree where we can perform binary search, which is particularly used to perform binary search. Such a tree is called binary search tree, basically. But to understand binary search tree, we first need to figure out what exactly is a tree. What kind of data structure is a tree? If you look at the cheat sheet obtained, you can, of course, always find all these with their Wikipedia links and what is the complexity when it comes down to any of these. But what is a tree to begin with? See guys, as you can see in real life, a tree is something that has roots at the bottom and leaves at the top. Just invert it. That's basically a tree in computer science. A tree in computer science is where root is at the top, leaves are at the bottom. Now, how does this make sense? Let me explain to you guys. Think about a double linked list. So when you talk about a double linked list, here's the basic idea. Each element can store one element to the next address and previous address. Instead of having first element storing previous as null, what we're going to do here is, let's have the first element, something like 10. It will store address of another element. Instead of previous, we call it as left. Instead of next, we call it as right. That's the basic idea. Instead of previous element, we call the previous element as left element, and the next element we'll call it as right element. So the left element of whatever you have your value, that is 10, can be something like 5. The right element towards it can be something like 15. The left, again, it can also have elements to the left and right, something like 12 or 7. It can also have something to the left and the right of 15, like 13 and 19. So this is basically a tree. The topmost element of the tree is called root, and we should always have this root's address, because only with the address of root I can get address of every other element. That's the basic idea. Without root's address, I can't get any other address element. So in this case of when you have a root, you have a lot of different kinds of questions you can expect within this. I'll just point out to just a few of them. I'll not be going through all of them because we can't do the whole concept of trees, binary search trees, and everything in a very short time. So before going ahead with this, the basic idea you guys just need to know is when it comes to a tree, the first root element, or whatever you call this as the first element, it will be stored at a level 0. The next elements are stored at a level 1, level 2, and so on. And the height of this tree is called height 3. Basically, you can get a lot of questions based on this, especially in MCQs, but we're not going to focus on that because I do not expect such questions when it comes to TCS Digital particularly. But if you guys are interested in learning more about this, I'll just point to a few things that you guys can go through and learn. That is, just search for properties of different types of trees. Like there are many different types of trees, like a complete tree or a pathological tree or a full binary tree, and so on. There are a lot of different types of trees. So one thing you guys basically need to know, if you really want to learn all of this, is just search this out. But our focus in our session is going to be on something else. That is, we're going to focus on how exactly we use binary search trees particularly. So here, binary search tree is where, think of it guys, if you want to search for an element, let's say this is my root element. If I want to search for an element, here's how I'm going to make sure I'll be able to search it. Every element to the left of the root should be lesser than root. Every element to the right of the root should be greater than root. So whenever I search for an element, I will be able to get to know whether, if I'm searching for something like, let's say 15, the first thing I'm going to do here is just search for that element over here and check if 15 is equal to the root. Now we know that 15 is not equal to the root. What? Instead, we know that 15 is greater than the root. Since it is greater than the root, we will not search in any element to the left of 15. We will only search for elements in the right of 10. So to do that, every element in the left of 10 must be lesser than it. So that means here, to the left of 5 also, this must be lesser than that. So I can take this up as, instead of 12, something like 3. So now every element to the left of 10 is lesser than it. Every element to the right of 10 is greater than it. Similarly here, every element to the left of 5 is lesser than it. Every element to the right of 5 is greater than it. So if I want to search for an element like 20, I'm going to first search if 20 is equal to root. 20 is not equal to root. 20 is greater than root. Since 20 is greater than root, I'm not going to search in the left part at all. I'm directly going to go to root's right address. Remember, root is 10. It will have a left address. It will have a right address. Since 20 is greater than 10, we will go to its right address. So when we go to the right address, we're going to start searching if this is equal to 20. Of course, this is not equal to 20. It's again lesser than 20. 20 is greater than 15. So we're going to cancel everything on the left, go for the right. So the basic idea of a binary search logic can be used in a binary tree logic as well. And in binary tree, it's easy for us to insert an element in the middle anywhere we want. That is why we use binary tree whenever you need to insert or delete elements instead of just a binary search. So this particular tree is called a binary search tree, where every element to the left is lesser and every element to the right is greater. I have one question. What's the difference between just a tree and a binary tree? See, When you talk about a tree, an element can have more than one value associated next to it. So we generally call this 10 as the parent node, and everything below it we call it as a children node. So I can have below 10 5, 8 and 15. So I have three children nodes for the node 10. So this is a, you can say, a tree which has three nodes for each node, maximum three nodes. So that cannot be a binary tree. Binary tree is where each node can only have two children at maximum. So followed by this, the next thing you need to know is, in a binary tree, in just a binary tree, each node can have any value. It can have 13, it can have 29, it can have 130, anything possible. That is a binary tree. But when you talk about a binary search tree, particularly when you talk about a binary search tree, the basic idea here is that every element to the left of a node will be lesser than it, and every element to the right of a node will be greater than it. That's the basic idea. I hope that makes it simple and easy for everyone to understand here. So with this logic, let us now go ahead and look at a few other questions that we can expect. So basic idea, you guys need to know what is a tree, what is a binary tree, and what is a binary search tree, and what else you need to know in order to get to know like time complexities. So we have already gone through big O cheat sheets, the one cheat sheets we have seen already. So I would suggest you guys to check those so that it becomes much easier for you to access or identify how you can get this info as well. So going ahead with this, here's the basic idea, guys. With this idea of trees, you have a couple of questions. That is, what are the some real case usage of all of these as well? So we have seen a use cases of many of these. Apart from this, you guys should also know that there are some other use cases for some of these data structures. For example, for those who don't know this notations, like if I have something like 10 plus 15 plus 20 or into 20, this is called an infix notation. We can convert this infix to either postfix or to prefix notation. So when we have postfix or prefix notation, we can solve them without requirement of brackets. For infix notation, we need to know which has higher priority. Multiplication has higher priority. But initially for computers to solve, we generally used postfix notations, and whatever infix notations was there, we converted to do postfix notation. Like to convert it, all we needed to do was a into b was just became a b into, and a plus b just became 15, oh sorry, 10, 15, 20 plus, because this is a plus and this is b. So this will be your postfix expression, or in short, in simple, a plus b just became ab plus. This was easy to solve for computers. So this is also called postfix or Polish notation as well. So to solve this, we used the concept of stacks as well. So these are used in many different ways. If you guys are interested in knowing these in detail, what I would suggest as well is use stacks are also used for postfix expression solving as well as prefix expression solving. Also, if you guys are interested, you can search something up called Tower of Hanoi, which is also solved using the same method as well. Now, let us go ahead and look at what questions can be expected further ahead within trees, and particularly within graphs and dynamic programming. So one of the question you can expect is, what is the real life application of trees? So this is something that if you guys are computer science students, you may have gone through a subject called compiler design. In compiler design, you create something called symbol tables. You may have observed this. So, or syntax analysis. So for all of these purposes, we use the concept of trees, even when it comes to English language. If you want to identify each sentence and divide it to different parts and identify each part of that sentence as well, we use some concept of trees as well, even in this, which is used in natural language processing or used in machine learning as well. I do have a request stating please go through videos on AI, ML, and IoT. Our next sessions are planned on those. Our next couple of sessions, that is tomorrow and day after tomorrow's sessions, are purely on all the recent trends that you can expect within your interviews. That is recent trends like um, artificial intelligence, machine learning, deep learning, Internet of Things, blockchain, cloud computing, and all of these. So we'll be going through as much of these as possible, and I'll be giving you guys a few practical um, examples for you guys to understand it better as well. So um, before we go ahead to that, let us go ahead in the concept or in the concepts that we are currently studying. So the basic things here, guys, all that you studied right now was about the basic kinds of data structures. Now, another basic kind of data structure that we do have is graphs. Now, when you talk about graphs, here's the basic idea. I'm just going to try to explain in short what it is, where we use it, and basically how it is used. Since we already got to know all about trees, from binary tree, binary search tree, and everything, so let us now go on to something ahead, that is graphs. And one more thing that you guys, if interested, if you find time, you guys can learn is in trees or in binary trees particularly, you have something called pre-order, in-order, and post-order traversals of binary trees. That is something I would suggest you guys to go through and learn, as that is also hugely important. So before I go for graphs, just in short, remember arrays are used whenever elements are stored in continuous memory location. So there are a lot of things like unfragmented memory in your hard drive. They are all stored in continuous memory locations. When you talk about stacks, we use them particularly in things like, we have seen the real life examples, that is undo, redo, and so on. And queues, we have already known online flash sales, ticketing systems, and so on. And when you talk about linked lists, things anywhere where you have to go to previous some different memory location and ahead to a different other memory location, a simple gallery that is in your phone, it goes through images of which are stored in different memory locations next when you swipe left and right. So that is an example where linked lists are also used in that. So followed by this, now let us go on to the concept of graphs. So I hope that helped it clear out a couple of questions that I've just received. So let's go on for this. See, guys, when you talk about graphs, here's the thing. Let's say there are 4 cities. Let's assume the city, I'll just give you guys the name of the city as 1, 2, 3, 4 for easier understanding. Now, if I want to go from first city to second city, there is a route. And the distance between first to second city, let's say, is 5 kilometers. If I want to go from second to third city, let's say there's a route that's again, let's say, 7 kilometers. And there's no other route to go from any other cities. If I want to go from third to fourth, there's a route, let's say the distance is just 2 kilometers. Now, I can't express this logic using something such as trees or anything like this. For this to explain this logic, to put this into memory so that our programs can understand, we need to use a very different data structure that is called graphs. And here's basically how it looks like. Think about an array, a two-dimensional array, where we will write the distance between all of these cities. So distance between 1 to 1 we know it's always 0, 2 to 2 we know it's always 0, 3 to 3 we know it's always 0, distance between 4 to 4 we know it's always 0. So you can say diagonal elements are basically 0. After diagonal elements are 0, let's look at the next one. 1 to 2 the distance is 5. So if I'm going from 1 to 2, distance is 5. If I'm going from 2 to 1 also, distance is 5. Then let's go 2 to 3, the distance is 7. And that is if I'm going from 2 to 3. If I'm going from 3 to 2 also, the distance is basically 7. And likewise, the last one we have 3 to 4. So if I'm going from 3 to 4, the distance we have is 2. Or if you're going from city number 4 to city number 3, distance is also 2. Now everywhere else you don't have any way to go. So in that places you can just give a random value, generally like -1, suggesting there's possibly no direct route. Or in some cases we put it up as 999 as well. So I'll just put it up as -1 in this case, stating that there's absolutely no route to go from all these cities. If you look at 4, from 4 to 1, if I want to reach, there's no location from 4 to 1. So the value we have in this matrix is -1. So this is your simple graph. Now here, this is called an undirected graph. If you guys see, this graph is symmetric. If you divide it into half, this half and this half are very symmetric. I have 5 and 5, -1 and -1, -1 and -1. Then I have 7 and 7, and again -1 and -1. So it is symmetric in nature. Whenever it is symmetric, you can say the reason it is symmetric is from 1 to 2, the distance is same as 2 to 1. When 3 to 2, the distance is same as 2 to 3. This is the basic idea. So with this, you guys can understand that in graphs, you have two types. One is called undirected graph, or in other words, I'll just call it as symmetric or undirected graph. And the other is asymmetric or directed graph. And these are created using matrices. Now, there is one more way to create them using a different technique. When I'll repeat this, using a different technique, this is where many of us don't know. There is another way of creating graphs when you do not have, in short, when you do not have things such as matrices. Because instead of 4 cities, what if you have 4,000 cities? Can you create a matrix and store that in a memory? Because if you have 4,000 cities, think about it. When you have 4,000 cities, you'll have 4,000 into 4,000, a graph, and each element is going to take, let's say, 4 bytes integer. So that's going to be such a huge amount of bytes taken. So it will be something around 800 to 800 MB or 1000 MB or something like that, I assume, if I'm not wrong. But if it is something so huge, you can't create a simple matrix like that. You need a different method. So I'll show you guys what will be the method to do that. But for now, just remember, a simple graph like this, where distance from 1 to 2 is same as 2 to 1, we call it as undirected or symmetric graph. But if distance between 1 to 2 is different, like for example, think of this, from 1 to 2 distance is 5, but if you want to go back from 2 to 1, distance is just 3. So 2 to 1 instead of 5, it becomes 3. Now this is not symmetric anymore. Similarly, let's take 3 to 2, the distance is 7, but if you're going from 2 to 3, distance is 6. So 2 to 3, distance is 6. Let's say the other one will make sure it remains as 2 itself. From 4 to 3, if you go, let's make it as 2 itself, let it be. So now it is asymmetric graph, because there is directions, there's different directions in each of the place. So this is called a directed or an asymmetric graph. That is the basic idea. So in this way, you have two ways to create these using matrices. That is, if it is symmetric undirected, you have one way. If it is asymmetric or directed, you have a different way. But when the data is large, or when the amount of data that you have is so huge that it's not easy to create a simple graph like this, the way we do it is using a different method that is called list. So to store graphs, we have two basic methods. The basic methods are, one is called adjacency matrix, and the other method is called adjacency list. So adjacency matrix, we just saw it. This is basically how we create it. But in an adjacency list, we don't use a matrix at all. Think about 5 cities. I have 1, 2, 3, 4, and 5. So I have a route from 1 to 2, that is 3, 2 to 3, that is 7, 3 to 4, that is 6, and 4 to 5, that is 5. So in this case, what we do is we create a list of elements. That is, the first element will store from 1 to 2, the direction is 3. Then the second element will store, think of this guys, the basic idea is if you're able to go from 1 2 3 4 5 so on like this, so you're just gonna state from 1 to 2 the distance is 3, and from 2 to 3 the distance is 7. You're going to store it as a list, this data. There won't be a matrix. If there's no matrix, there's so much space saved. So for these purposes, we use something called adjacency list as well. So these are the two different methods using which we create graphs. Now when you talk about these graphs, this is where we start coming into the concept of algorithms. But before going into the concept of algorithms, let me just point out a simple thing. Like, where are we going to use this? Where exactly will we use the concept of graphs? So when you talk about a graph, think about this, guys. You may have a software which tells you which is the best way to travel all the cities with the least money spent, or which is the best way to travel all the city with the least fuel spent using the list of data you have. So such questions are generally asked in your technical interviews, but it's not something we need to know now. But you guys need to know that such questions are asked in interviews, and you have algorithms to solve them as well. But before we go on, I'm going to introduce you to a concept called dynamic programming within a minute in short, just a minute or two. So if I'm calculating Fibonacci series, I'm just going to give you guys this simple example. Think about this, guys. If I want to calculate fourth Fibonacci number, what do? We have our logic. First Fibonacci number is 0. Second Fibonacci number is 1. The rest we don't know. The rest we will calculate. So if I want to calculate fourth Fibonacci number, the first thing I need to do is fourth Fibonacci number is sum of third Fibonacci number and second Fibonacci number. And third Fibonacci number is again sum of second Fibonacci number plus first Fibonacci number. I'm just going to use plus here so that we can get to understand. Second Fibonacci number is sum of first Fibonacci number of 1 and Fibonacci number of 0. So we basically know Fibonacci number of 1. I'll just point it out like this. Fibonacci number of 1 or Fibonacci number of 0 should always give you 0. Fibonacci of number of 1 should always give you 1. So Fibonacci of number of 1, we know the result is 1. Fibonacci number of 0, we know the result is 0. So we don't need to divide it further on. But here also Fibonacci of 2, I'll have to do the same thing. I'll have to divide it as Fibonacci of 1 and Fibonacci of 0. Now, if you guys observe, are we not repeating some steps here? Think about this. Fibonacci of 2 divided into 1 and 0. Calculated. Fibonacci of 2 again here divided into 1 and 0. We are performing this calculation 2 times. When you increase the size of the Fibonacci number from 4 over to 5 to 6 to 7 or so on, if you want to find 50th Fibonacci number, you see that a lot of these steps are repeated. lot of these steps are repeated. You are calculating them again and again. Now that is a waste of time and space both to do that. So to make it better, what we can simply do, instead of, see, you're calculating Fibonacci of 2 once here and 2 times here. Minimum you're calculating it twice. So instead of doing all of this, what we are going to do here is, if I want to calculate fourth Fibonacci term, I'm just going to take an array of indices 0, 1, 2, 3, and 4. And all that I'm going to do here is just say that Fibonacci of 0 is 0, 1 is 1. Fibonacci of 2 will be sum of these two, that is 1. Fibonacci of 3 will be sum of these two, that is 2. And Fibonacci of next one will be sum of these two, that is 3. So when you look at this, the value you receive here is 3, which you found out by calculating Fibonacci of 2 only once. You didn't have to calculate this multiple times. So that is the basic advantage of dynamic programming. So dynamic programming is where any sub function, you don't have to calculate it multiple times. You only have to calculate it once. So the idea of dynamic programming is any sub function is only performed once uniquely. It is never performed more than once. This is the basic idea you guys need to know, and you guys have the example of Fibonacci to understand it as well. If you guys want to learn in depth about this, there are a couple of types of it. That is, we divide it into memorization and tabulation. If you guys are interested to learn more about it, you guys can go through and check these out. But now, for now, I'm just going to focus on a couple of simple things, guys. Followed by this, you guys have the next thing called algorithms, which I'll touch upon in the next session also a little. But before going on to the next session, I'm just going to want to go through this a little this session. See guys, when you talk about algorithms, there are many different kinds of algorithms. There are, as you guys know, searching algorithms, sorting algorithms. Then there are things like your divide and conquer algorithm. There are things that we choose particularly, like things like salesman problems or hash function algorithm. There are so many algorithms that you guys can go through. I will be giving you guys an introduction to what are the different algorithms, what are the kinds of algorithms that you're going to have, and which one you should use at what time. And you guys already know the time complexity for most of them anyway, so I don't think I have to go through that a lot. So I'm going to touch upon this slightly, followed by going through all the recent trends. And this is where I can expect a lot of questions to be asked. I'll tell you guys, in TCS Digital, they have already tested your logical ability by now. The next thing they're going to test is, what do you know about the technologies that they will be using in their company? What do you know about the technologies that will be used in the future currently to develop programs and so on? So all of these are present in something called recent trends, which we will focus on in the coming sessions. So please make sure you guys do go through the coming videos without a doubt. And for more videos, for more contents, check out our other videos. Hit the like button, subscribe, and go through as much as possible. So I hope before we end the session, today's session was useful on introduction to data structures mainly, and a few algorithms, and what questions you can expect from them. So let me know guys what you thought about the session and how you guys felt over the live chat. And that'll be a huge thing to understand, in order to make sure that if you have any questions, I'll go through that. Or if you guys felt like, yes, this was pretty good enough, we were able to understand something new, and this will help us go through the coming sessions as well as digital interviews with more confidence, we are very happy to hear that. So let me know guys whatever you guys felt, or if you guys have any questions, I'll make sure to take it up. And by the time, I'll make sure to share the link for today's session so that you guys can access it and use the same DSA for digital. I'm just going to share the link here for you guys. So by the time, you guys can let me know if there's any particular thing that you guys want us to go through in the coming sessions for digital. And some of you have pointed out towards recent trends in particular. We're going to go through all of those. And you guys also can also feel free to point out how you felt. What do you guys think? And it's always good to hear your feedback at any point of time. Thanks at Adarsh and Sandeep for the nice words. So guys, I'll be sharing the link in chat, and we'll be sharing the link in the chat in just a couple of minutes. So please hold on for that so you can access it and use it as well. And at the same time, know that in the coming sessions, we'll be going through different algorithms as well as just a small introduction to this. And followed by this, we will be going through mainly the major part, that is recent trends, including AI, ML, deep learning, IoT, cloud computing, big data analytics, and a few other things, including blockchain. So we'll go through all of these, which can be expected, and make sure you guys do check out those videos. And thank you for being a part of this 2 hour session, guys. Have a good time and good luck. So I have a question before that. What is the real-time examples of trees and graphs? See, when you talk about trees, the basic idea is you can't store everything in continuous memory location. You have to store them in different locations. So trees is where you start to store, you start to feel like in an arrays, everything must be stored in continuous memory location. But if the elements are too much and you insert and delete them a lot, you end up basically using trees. So that's the basic idea. So in graphs, we use these particularly for calculations in terms of distances and so on. So like the one we saw a few examples ago. But I'll also be going through a few more examples in algorithms, particularly just a couple of examples in the next session, so you can understand where graphs are used more. So we'll make sure to do that. All right, students, thank you. Have a good time. And do check more of our videos for more content. Thank you, guys.